Hello everyone. Today let's continue with proofs. The first topic for today's class is proof by cases. Before I show you what it is, let's look at an example first. Let x be an integer. Show that x squared plus 3x plus 2 is always even. If we try to prove this number is even directly, it's not easy. But we can consider x in different cases. Since x is an integer, it could be either even or odd. So we can consider this problem in two different cases. If there are finitely many cases, and we verify each case individually, that's called proof by cases. If there are finitely many cases, and we can verify each case individually, that's called proof by cases. So here, let's prove by cases. Let's prove this problem by cases. Since s is an integer, it could be either even or odd. Case 1, let's consider x is even. If s is even, then s equal to 2k. Where k is an integer. Then s squared plus 3x plus 2, that can be written as 2k squared plus 3 times 2k plus 2. If I simplify, I get 4k squared plus 6k plus 2. Then for these three numbers, I can factor 2 out. If I pull out 2, I get 2k squared plus 3k plus 1. And we know that since k is an integer, 2k squared plus 3k plus 1 must be an integer. Since x squared plus 3x plus 2 equal to 2 times the integer, then this must be an even number. So x squared plus 3x plus 2 is even. So when s is even, I show that this number x squared plus 3x plus 2 is even. Case 2. Let's consider s is odd. Case 2, let's consider s is odd. If s is odd, then s can be rewritten as 2k plus 1. Where k is an integer. If s is odd, then s equal to 2k plus 1, where k is an integer. Then I can plug in 2k plus 1 into this equation here, into this function here. S squared plus 3x plus 2. If I plug in 2k plus 1 for x, I have 2k plus 1 squared plus 3 times 2k plus 1 plus 2. If I expand a perfect square, I have 4k squared plus 4k plus 1. If I distribute 3, I get 6k plus 3 plus 2. Then I can combine like terms. If I combine like terms, I get 4k squared plus 10k plus 6. Then for this number, I can factor 2 out. If I pull out 2, I have 2k squared plus 5k plus 3. Since k is an integer, then 2k squared plus 5k plus 3 must be an integer. Since s squared plus 3x plus 2 equal to 2 times the integer, this must be an integer. This must be an even number. So s squared plus 3x plus 2, it must be even. Since in both cases, we can prove that s squared plus 3x plus 2 is even, then this number s squared plus 3x plus 2 must be even. if in all cases we get the same conclusion, then this conclusion must be true. If in all possible cases we get the same conclusion, then this conclusion must be true. Therefore, x squared plus 3x plus 2 is even. Since in all cases we get the same conclusion, then this conclusion must be true. Therefore, x squared plus 3x plus 2 is even. So for proof by cases, keep this idea in mind. If there are finitely many cases, and every case will lead to the same conclusion, then this conclusion must be true. That's called proof by cases. Next example, let a and b be real numbers. Show that absolute value of a times b equal to the absolute value of a times the absolute value of b. So for absolute value, there's one property, keep it in mind. If s is greater or equal to 0, then absolute value of x is equal to x. If s is less than 0, then absolute value of x equal to negative x. That's the property of absolute value. If s is greater or equal to 0, then absolute value of x equal to x. If s is less than 0, then absolute value of x equal to negative x. That's a property about absolute value. Keep this idea in mind. Now, for proofs about absolute value, let's consider positive and negative numbers. For numbers a and b, there are 4 different cases. Could be a is positive, b is positive, or a is positive, b is negative, or a is negative, b is positive, or a is negative, b is negative. There are 4 different cases. So we can prove by cases here. Let's consider positive and negative numbers. Case 1. A is greater or equal to 0, and b is greater or equal to 0. If a is greater or equal to 0, b is greater or equal to 0, then a times b, then a times b must also be greater or equal to 0. Since a is greater or equal to 0, b is greater or equal to 0, then a times b must be greater than or equal to 0. So, since a times b is greater or equal to 0, then when we take absolute value, for positive number, it stays the same. Since a is greater than or equal to 0, then absolute value of a equal to a. Since b is greater or equal to 0, then absolute value of b equal to b. So if I multiply left side to the left side, right side to the right side, absolute value of a times absolute value of b equal to a times b. That's the same as absolute value of ab, since ab equal to absolute value of ab. So absolute value of a times absolute value of b equal to absolute value of ab. So in case 1, we get a conclusion here. Absolute value of ab equal to absolute value of a times absolute value of b. That's case 1. Case 2. A is positive, b is negative. Case 2. A is greater or equal to 0, b is less than 0. Then, if I multiply a and b, a times b must be less or equal to 0. If I multiply a times b, it must be less than or equal to 0. So, this is a negative number. When I take absolute value for ab, I get negative ab. For negative number, when I take absolute value, I get negative of this number. So when I take absolute, since ab is less than 0, when I take absolute value, it becomes negative ab. Then, since a is greater or equal to 0, then absolute value of A equal to A. Since B is less than 0, then absolute value of B equal to negative B. So if I multiply left side to the left side, right side to the right side, I have absolute value of A times absolute value of B equal to negative AB. And we know that negative AB is the same as absolute value of AB. So absolute value of A times absolute value of B equal to absolute value of AB. So in case 2, we get the same conclusion here. Next, case 3. Case 3, A is negative, B is positive. A is less than 0, and B is greater than or equal to 0. Then if I multiply AB, negative number times positive number must be negative. Negative number times positive number, it must be negative number. A is less than 0, B is greater than 0, negative number times positive number must be negative. So since AB is less than 0, it's negative. When I take absolute value for AB, I get negative AB. Since AB is negative number, when I take absolute value, I get negative AB. Since A is less than 0, then absolute value of A is negative A. Since B is greater or equal to 0, then absolute value of B equal to B. Since B is greater or equal to 0, absolute value of B equal to B. So if I multiply left side to the left side, right side to the right side, absolute value of A times absolute value of B equal to negative AB. And we know that negative AB is the same as absolute value of AB. So absolute value of A times absolute value of B equal to absolute value of AB. So in case 3, we get the same conclusion. In case 3, we get the same conclusion here. Case 4. They are both negative. A is less than 0 and B is less than 0. Case 4. A is less than 0 and B is less than 0. If they are both negative, if A is negative, B is negative, then when I multiply AB, if they are both negative, when I multiply AB, I get positive number. Negative number times negative number is positive. AB is greater than 0. So absolute value of AB, since A times B is positive, absolute value of AB is the same as AB. For positive number, absolute value of AB stays the same. Since A is less than 0, then absolute value of A equal to negative A. Since A is less than 0, absolute value of A equal to negative A. Since B is less than 0, then absolute value of B equal to negative B. If I multiply left side to the left side, right side to the right side, then absolute value of A times absolute value of B equal to A times B. Because double negative is positive. Negative A times negative B equal to AB. Double negative is positive. So AB is the same as absolute value of AB. This AB is the same as absolute value of AB. So absolute value of A times absolute value of B equal to absolute value of AB. So here in all four cases, we get the same conclusion. There are only 4 cases. For real numbers A and B, there are only 4 cases, and we verify all 4 cases. They all lead to the same conclusion here. They all lead to the same conclusion. Then this conclusion must be true. Since in all 4 cases we get the same conclusion, then this conclusion must be true. Therefore, absolute value of A times absolute value of B equal to absolute value of A, B. Since in all 4 cases we're going to say conclusion, this conclusion must be true. There are only 4 cases, and in all 4 cases we're going to say conclusion. This conclusion must be true. Next example, let A and B be real numbers. Show that absolute value of A minus B equal to the absolute value of B minus A. So we know for absolute value, there's 2 properties. If x is greater or equal to 0, then absolute value of x equal to x. If x is less than 0, then absolute value of x is negative x. So for absolute value, if x is positive, then absolute value of x equal to x. If x is negative, then absolute value of x equal to negative x. So for this problem, we can also consider positive and negative numbers. If A is greater than B, then this number is positive. But if A is less than B, then this number is negative. So consider in 2 cases. Let's consider in 2 cases. Case 1. A is greater than B. If A is greater than B, then this is positive. If A is less than, case 2, we can consider A is less than B. If A is less than B, then this will be negative. We can apply the property of absolute values. Case 1, if A is greater or equal to B, then A minus B, larger number minus smaller number is positive. If A is greater than B, then larger number minus smaller number is positive. And B minus A will be less than 0. Smaller number minus larger number will be less than 0. Smaller number minus larger number is negative. Larger number minus smaller number is positive. Smaller number minus larger number is negative. So since A minus B is greater or equal to 0, then absolute value of A minus B equal to A minus B. For positive number, absolute value of this number stays the same. For any positive number, when we take absolute value, it stays the same. Since B minus A is less or equal to 0, then when we take absolute value for negative number, add negative sign in the front. When we take absolute value for negative number, this number is negative. When we take absolute value for negative number, add negative sign in the front. We get negative B minus A. Negative B minus A, if I distribute, is the same as A minus B. If I distribute, it's the same as A minus B. So they are both A minus B. So A, absolute value of A minus B equal to A minus B. Which is the same as absolute value of B minus A. So absolute value of A minus B equal to absolute value of B minus A. That's case 1. We get this conclusion here. Now case 2, A is less than B. Case 2, A is less than B. For any real numbers A and B, there are only 2 cases. Either A is greater than B or A is less than B. Case 2, if A is less than B, then smaller number minus larger number. Smaller number minus larger number is negative. And larger number minus smaller number is positive. Larger number minus smaller number is positive. Smaller number minus larger number is negative. Larger number minus smaller number is positive. Since A minus B is less than 0, that means it's negative, then when we take absolute value for a minus b, absolute value of negative number, for absolute value of negative number, we add negative sign in the front. For absolute value of negative number, we add negative sign in the front. This is equal to negative a minus b. If I distribute negative sign, that's b minus a. Since b minus a is greater than 0, since b minus a is greater than 0, this is positive number, then when we take absolute value for positive number, it stays the same. Since b minus a is positive, when we take absolute value for positive number, it stays the same. So you can see that here, they are exactly the same. So absolute value of a minus b equal to b minus a, which is the same as absolute value of b minus a. So absolute value of a minus b equal to absolute value of b minus a. In both cases, we get the same conclusion. Therefore, this conclusion must be true. There are only two cases, and in both cases, we get the same conclusion. This conclusion must be true. Therefore, absolute value of a minus b equal to the absolute value of b minus a. Next example. Let a and b be real numbers. Show that the maximum of a b plus the minimum of a b equal to a plus b. Let a and b be real numbers. Show that maximum of ab plus minimum of ab equal to a plus b. So for maximum of ab, we choose a larger one from here, from a and b. For minimum of AB, we choose a smaller number from AB. We try to show that maximum number of AB plus minimum number of AB equal to A plus B. So here we can also try to prove by cases. For real numbers A and B, either A is larger than B or A is less than B. Prove by cases. Case 1. A is greater or equal to B. Case 1. A is greater or equal to B. If A is larger than B, then the maximum of AB equal to A. If A is larger than B, when I take a maximum from these two numbers, I take A. The minimum of AB. For the minimum of AB, I pick the smaller one. Since A is larger than B, B is smaller, so I pick B. Since B is smaller, I pick B. So maximum of A, B. Add left side to the left side and right side to the right side. Maximum of AB plus minimum of AB. If I add left side to the left side, I get maximum of AB plus minimum of AB. If I add the right side to the right side, I get A plus B. So that shows maximum of AB plus minimum of AB equal to A plus B. We get a conclusion here. Case 2. A is less than B. If A is less than B, then that means A is smaller, B is larger. Then the maximum of AB, since B is larger, for maximum of AB I take B. For minimum of AB, since A is smaller, so for minimum of AB, I take A. Since A is smaller, B is larger. So for maximum of AB, I take B. For the minimum of AB, I take A. So if I add the left side to the left side, right side to the right side, I have maximum of AB plus minimum of AB equal to B plus A, which is the same as A plus B. So in both cases, we get the same conclusion. Then this conclusion must be true. Therefore, maximum of AB plus minimum of AB equal to A plus B. Next, let me introduce mathematical induction. In order to show a statement P of n is true for all n, usually is all positive integer n. Is true for all n. Usually is true for all positive integer n. The proof by mathematical induction. The proof by mathematical induction consists two steps. The proof consists of two steps. First step is called a basis step. First step is called a basis step. In the basis step, we verify that the statement P of n is true for the first n value. In basis step, we verify that the statement P of n is true for the first n value. That's called a basis step. Next step is called inductive step. In the inductive step, show that P of k always implies P of k plus 1. In the inductive step, show that P of k always implies P of k plus 1. So, assume P of k is true. Try to prove that P of k plus 1 is also true for all k. The idea for mathematical induction is that we try to prove that P of n is true for all positive integer n. Let me try to prove that P of 1 is true, P of 2 is true, P of 3 is true, P of 4 is true, P of 5 is true, P of 6 is true, and so on. The statement P of n is true for every positive integer n. Now, basic step, verify that P of n is true for the first n value. Basic step verify that P of n is true for the first n value. P of 1 is true. Then inductive step shows that if P of 1 is true, if P of k is true, then P of k plus 1 is true. That means if P of 1 is true, then P of 2 is true. If P of 2 is true, then P of 3 is true. Because P of k implies P of k plus 1. If P of 2 is true, then P of 2 plus 1 is also true. Then, if P of 3 is true, then P of 3 plus 1 is true. By inductive step, we can show that if P of 4 is true, then P of 4 is true. If P of 4 is true, then P of 6 is true. So by inductive step, we can show that this statement P of n is true for all integer n. By basic step, we show that P of 1 is true. Then by inductive step, we can show that P of 1 implies P of 2 is true. P of 2 is true implies P of 3 is true, and so on. P of n is true for all n. That's the basic idea of mathematical induction. Next, let me show you an example. Show that 1 plus 2 plus 3 plus plus n equal to n times n plus 1 over 2 for all integer n. Greater than or equal to 1. Show that 1 plus 2 plus 3 plus n equal to n times n plus 1 over 2 for all integer n. Let's try to prove it by mathematical induction. So before the proof, I first of all try to write the left side in sigma notation. Before the proof, I first of all try to rewrite the left side in sigma notation. 1 plus 2 plus 3 plus n. This can be written as sigma I from 1 to n of I. Left side can be rewritten as sigma. Left side can be rewritten in this form in sigma notation. I varies from 1 to n. When I is 1, we have 1 here. When I is 2, I have 2 here. When I is 3, I have 3 here. When I is n, I have n here. Sigma means addition. So rewrite this expression in sigma notation. Prove this equal to this by mathematical induction. So for the basis step, we verify that this statement is true for the first n. First n is n equal to 1. When n equal to 1, left hand side, when n equal to 1, left hand side equal to the sigma I from 1 to 1 of I. When n is 1, I have I from 1 to 1. If I varies from 1 to 1, this I must be 1. So left hand side equal to 1. How about the right hand side? Right hand side, we also plug in 1 for n. If I plug in 1 for n, I have 1 times 1 plus 1 over 2. 1 times 1 plus 1 is 2. 2 over 2 is 1. So here, left hand side equal to the right hand side. So left hand side equal to the right hand side. So when n equal to 1, this statement is true. When n equal to 1, this statement is true. That's the basic step. Here we complete the basic step. Next, for the inductive step, we assume the statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. So assume this statement is true when n equal to k. So assume this statement is true when n equal to k. That means summation I from 1 to k of I equal to k times k plus 1 over 2. Assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. And since this is true, the left side, I can write it back in this form. I can write the left side back in this form. And this can be rewritten as 1 plus 2 plus 3 plus k equal to k times k plus 1 over 2. I can write the left side in standard form. 1 plus 2 plus 3 plus k equal to k times k plus 1 over 2. This is called the induction hypothesis. 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 Now, we try to prove this statement is also true when n equal to k plus 1. Now, when n equal to k plus 1, left hand side equal to this I from 1 to k plus 1. When n equal to k plus 1, we plug in k plus 1 here. Left side is I from 1 to k plus 1. If I expand this I values from 1 to k plus 1, if I expand this sigma notation, I values from 1 to k plus 1. That's 1 plus 2 plus 3 plus all the way to k plus 1. And the previous term is k. Since I values from 1 to k plus 1, the term before k plus 1 must be k. Since I values from 1 to k plus 1, the term before k plus 1 must be k. Then, by induction hypothesis, this part, 1 plus 2 plus 3 plus k, by induction hypothesis, this part equal to k times k plus 1 over 2. By induction hypothesis, this part equal to k times k plus 1 over 2. And keep the last term the same. This is induction hypothesis. This step comes from induction hypothesis. 1 plus 2 plus 3 plus k equal to k times k plus 1 over 2. Then, if I try to add this together, this is a fraction, this is a whole number. I must put this over 1. Then find common denominator, which is 2. I multiply top and bottom by 2. So this expression can be rewritten as k times k plus 1 over 2 plus 2 times k plus 1 over 2. I put this term over 1. Then common denominator is 2. I multiply top and bottom by 2. That can be noted as 2 on the bottom. On the top, I can factor pull out k plus 1. On the top, if I factor pull out k plus 1, I have k plus 2. On the top, if I factor pull out k plus 1, what's left is k plus 2. That's the left hand side. Next, I try to show the right hand side. For the right hand side, when n equal to k plus 1, I plug in k plus 1 for each n here. Right hand side equal to k plus 1 times k plus 1 plus 1 over 2. For the right hand side, when n is k plus 1, I plug in k plus 1 for each n. I get k plus 1 times k plus 1 plus 1 over 2. If I simplify, that's k plus 1 times k plus 2 over 2. So here you can see that left hand side and right hand side, they're exactly the same. So left hand side equal to the right hand side. When n equal to k plus 1, I prove that left hand side equal to right hand side. Let's complete the proof by mathematical induction. When n equal to k plus 1, I prove that left hand side equal to right hand side. Let's complete the proof by mathematical induction. Next example, show that 1 cube plus 2 cube plus 3 cube plus n cube equal to n squared times n plus 1 squared over 4 for all integer n greater than or equal to 1. So here, let me first of all rewrite the left side in sigma notation first. Left side can be rewritten as sigma I from 1 to n of I cube. When I is 1, I get 1 cube. When I is 2, I get 2 cube. When I is 3, I get 3 cube. When I is n, I get n cube. That's the left hand side. And that's the right hand side. Proof by induction. I first of all try to verify that this statement is true when n equal to 1. This statement is true from the first n, which is n equal to 1. So the basic step, verify that this statement is true from the first n, which is n equal to 1. Basic step, verify that this statement is true for the first n, which is n equal to 1. When n equal to 1, left hand side, I plug in 1 here for n. Left hand side is sigma 1 I from 1 to 1, I cube. Since I varies from 1 to 1, I must be 1. If I plug in 1, I get 1 cube, which is equal to 1. So left hand side equal to 1. How about on the right hand side? For the right hand side, I plug in 1 for n. I get 1 squared times 1 plus 1 squared over 4. 1 squared is 1. 1 plus 1 is 2. I get 1 times 2 squared over 4. 2 squared is 4. 4 over 4 is 1. So left hand side equal to the right hand side. So when n equal to 1, left hand side equal to the right hand side. That's the basic step. That's the basic step. Next, for the inductive step, assume this statement is true when n equal to k. Assume this statement is true when n equal to k. So assume sigma I from 1 to k of I cube equal to k squared times k plus 1 squared over 4. Assume this statement is true when n equal to k. Then I can write this. I can expand the left side. I varies from 1 to k, so I have 1 cube plus 2 cube plus 3 cube plus k cube equal to k squared times k plus 1 over 2 squared, k plus 1 squared over 4. K squared times k plus 1 squared over 4. This is the induction hypothesis. This is the induction hypothesis. We try to prove that this statement is also true when n equal to k plus 1. We try to prove that this statement is also true when n equal to k plus 1. When n equal to k plus 1, from the left hand side, I plug in k plus 1 for n. I plug in k plus 1 for n. So I varies from 1 to k plus 1 of I cube. That's the left hand side. So if I expand this sigma notation, if I expand this notation, I have 1 cube plus 2 cube plus 3 cube plus k plus 1 cube from 1 to k plus 1. And the term before k plus 1 cube must be k cube. That's the term before k plus 1 cube. Then, by induction hypothesis, 1 cube plus 2 cube plus 3 cube plus k cube, this is equal to k squared plus k plus 1 squared over 4. This is k squared times k plus 1 squared over 4. Last term stays the same, k plus 1 cube. This step is because of induction hypothesis. Here we use induction hypothesis, I get this. Then we try to add these two terms together. This is a fraction, this is whole number, put it over 1. Find the common denominator, which is 4. Then we multiply the top and the bottom by 4. I have k squared times k plus 1 squared over 4 plus 4 times k plus 1 cube over 4. Put it over 1, then multiply top and the bottom by 4. Now I have same denominator. Common denominator is 4. For the numerator, I can factor. K plus 1 is a common factor. K plus 1 is a common factor I can pull out. Pull out k plus 1 squared. If I pull out k plus 1 squared, what's left is k squared plus 4 times k plus 1. If I pull out k plus 1 squared, what's left here is k squared plus 4 times k plus 1. Since I pull out k plus 1 squared, what's left here is k plus 1. Then, simply for the numerator, I have k plus 1 squared, k plus 1, here k squared plus 4 times k plus 1. I distribute 4. I get k squared plus 4k plus 4 over 4, which is k plus 1 squared. K squared plus 4k plus 4 is k plus 2 squared. If I factor this, that's k plus 2 squared over 4. That's the left hand side. Now the right hand side. For the right hand side, we plug in k plus 1 for n. Plug in k plus 1 for each n. Right hand side is k plus 1 squared times k plus 1 squared over 4. For the right hand side, I plug in k plus 1 for each n here. I get k plus 1 squared times k plus 1 squared, which is k plus 1 squared times k plus 2 squared over 4. So they are exactly the same. Left hand side equal to the right hand side. Let's complete the proof by induction. Let's complete the proof by mathematical induction. Here, left hand side equal to the right hand side. Let's complete the proof by mathematical induction. Next example, show that n squared is greater than 3n plus 5 for all n greater than or equal to 5. Proof by induction. We first of all try to verify that this statement is true for the first n. For the basic step, we try to verify that this statement is true for the first n. Here, first n is n equal to 5. Here, first n is n equal to 5. We try to verify that this statement is true for the first n. When n equal to 5, left hand side is 5 squared, which is 25. Right hand side is 3 times 5 plus 5. 3 times 5 is 15. 15 plus 5 is 20. So left hand side is greater than right hand side. Here, left hand side 25 is greater than 20. So left hand side is greater than right hand side. That's the basic step. Next, inductive step. Next is the inductive step. Assume this statement is true when n equal to k. So we assume k squared is greater than 3k plus 5. We assume this statement is true for the first k. We assume the statement is true when n equal to k. Since n is greater than or equal to 5, k must also be greater than or equal to 5. Assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. We try to prove that this statement is also true when n equal to k plus 1. So here, take this as my induction hypothesis. When n equal to k plus 1, we try to show left hand side is greater than right hand side. Or we can show that right hand side is less than left hand side. Either show that left hand side is greater than right hand side, or right hand side is less than left hand side. Either way is okay, but usually we start from the side that looks more complicated. Here, the right hand side looks more complicated. It has two terms. So start from the right hand side. Start from the side that looks more complicated. Let me start from right hand side. I try to show it's less than left hand side. When n equal to k plus 1, we try to show that k plus 1 squared is greater than 3 times k plus 1 plus 5. That's our goal. We try to prove this. When n equal to k plus 1, we try to show that k plus 1 squared is greater than 3 times k plus 1 plus 5. So this right hand side looks more complicated. I start from right hand side. Right hand side here equal to 3 times k plus 1 plus 5. This can be rewritten as 3k plus 3 plus 5. Since I try to use the induction hypothesis, I try to write 3k and 5 together. So this can be rewritten as 3k plus 5 plus 3. By induction hypothesis, 3k plus 5 is less than k squared. By induction hypothesis, 3k plus 5 is less than k squared. So this is less than k squared plus 3. By induction hypothesis, 3k plus 5 is less than k squared. Number 3 stays the same. Next, I try to make this looks like this. K squared plus 3 can be rewritten as k squared plus 2 plus 1. K squared plus 3 can be rewritten as k squared plus 2 plus 1. Since k is greater than 5, since k is greater or equal to 5, then 2k will be greater or equal to 10. Since k is greater or equal to 5, 2k will be greater or equal to 10. Hence 2k is greater than 2. Since k is greater or equal to 5, then 2k is greater than 10. Then 2k is greater than 2, since 10 is greater than 2. So this is less than k squared plus 2k plus 1. Because 2 is less than 2k. The first term stays the same, last term stays the same. 2 is less than 2k. So this is less than this expression. That can be rewritten as k plus 1 squared. That's the left hand side. So we see that here, right hand side is less than left hand side. Right hand side is less than left hand side, which means left hand side is greater than right hand side. That completely proved by mathematical induction. Next example, show that n factorial is greater than n squared for all integer n greater than or equal to 4. Let's prove it by mathematical induction. First of all, verify that this statement is true for the first n. That's called a basis step. Basis step. When n equal to 4, verify that this statement is true when n equal to 4. When n equal to 4, left hand side is 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24. Right hand side is 4 squared. 4 squared is 16. So left hand side is greater than right hand side. So when n equal to 4, left hand side is greater than right hand side. That's the basic step. Next, inductive step. For inductive step, we first of all assume this statement is true for n equal to k. Assume this statement is true when n equal to k. That means we assume k factorial is greater than k squared for all k greater or equal to 4. Assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. So take this as induction hypothesis. Take this as induction hypothesis. Try to prove that this statement is also true when n equal to k plus 1. When n equal to k plus 1, we either try to show that left hand side is greater than right hand side, or right hand side is less than left hand side. Either show that left hand side is greater than right hand side, or right hand side is less than left hand side. Either way is okay. But here, s squared, let's start from right hand side, s squared. Because when we plug in k plus 1, get k plus 1 squared, this part is more complicated. So start from the side that looks more complicated. Start from the side that looks more complicated. So here I try to show right hand side is less than left hand side. Here I try to show right hand side is less than left hand side. When n equal to k plus 1, right hand side is k plus 1 squared. That can be rewritten as k squared plus 2k plus 1. K plus 1 squared can be rewritten as k squared plus 2k plus 1. By induction hypothesis, k squared is less than k factorial. K squared is less than k factorial. So keeping the rest the same. K squared is less than k factorial plus 2k plus 1. K factorial is less than k factorial. So k squared is less than k factorial. Keep 2k plus 1 the same. Keep 2k plus 1 the same. Next, we know that 1 is less than k because k is greater than 4. Then k is greater than 1. Hence number 1 is less than k. So I keep the first term the same, second term the same. If I change 1 to k, this is greater than this. This expression here is greater than this expression. Two k plus k is 3k. Two k plus k is 3k. That's equal. This is equal sign. 2k plus k is 3k. And 3k is less than k factorial. K is less than k factorial. K is less than k factorial. So this expression is larger than this expression here. K factorial plus 3k factorial is 4k factorial. K factorial plus 3k factorial is 4k factorial. Since k is greater or equal to 4, k plus 1 is strictly greater than 4. Since k is greater than 4, then k plus 1 is greater than 4. So if I replace 4 with k plus 1, this is larger than this. If I replace 4 with k plus 1, this is larger than this. K factorial stays the same. K plus 1 is greater than 4. K plus 1 times k factorial is k plus 1 factorial. That's the left hand side. So right hand side is less than left hand side. So right hand side is less than left hand side. Let's complete the proof by induction.